Hey everyone. Today we'll be talking about malware classification through machine learning, specifically how we enhance known techniques with kernel emulation telemetry. So brief roadmap is that we touch on, let's say, known techniques in a public space that based mostly on a static analysis of malware file. Then we touch briefly limitations and why this does not provide a full picture to the ML algorithm. And then we will transit to a hybrid approach, and we will cover specifically techniques behind AI modeling, embeddings and 1D convolutions, because I assume since applicability of AI to security is bilingual problem, you need to know security and AI. I assume not much background in AI technology, so we will cover them briefly. Disclaimer, due to affiliation, since I'm a software engineer in Microsoft, this research doesn't represent functionality of MDE, just in case there will be correlations. It's a separate team work, and so far we know it doesn't reflect any models used in MDE. It's more of a public research we are contributing to the known techniques in this domain. Starting with what we know, how ML works for malware classification. Already a long time ago, right, for AI research 5 years back is huge time. There was released a great work by researchers in Endgame, originally, which later was acquired by Elastic. They now maintain this project. It's called Ember, and it basically describes a way to extract features from a PE file, portable executable file, as a byte blob. It's open source. You can take a look, and it captures around a dozen types that kind of extracts valuable information from PE file, like section info, imports info, entropies, byte histograms, etc. However, this has its own limitations. In fact, this feature extraction scheme works really well if we apply it to the general, let's say, malware threat landscape. However, there are ways to circumvent how this works. One of them is adversarial machine learning, which came to the acknowledgement of the field from computer vision. Back in 2014, the evasion attacks were presented. A little bit earlier, there were poisoning attacks. And how it basically works is that we modify an input to an ML model in some clever way. We generate perturbations, and it completely screws up how ML model behaves. In this example that was presented in the original paper, we see how seemingly random noise can completely circumvent the functionality of image classifier back then. This applies to the ML world in malware as well. For instance, there is a group in University of Cagliari published an attack of section injection, and when you add benign sections to already packed malware, already compiled malware, it in fact evades static classifiers with a high evasion ratio. The second problem with the static classifiers are packers, and for static classifier packed software and benignware and malware seems sort of the same, because a lot of properties that static classifiers extract become ubiquitous amongst the malware distribution. So where we can go from here? At this stage of ML applicability, at least in a public space, we know that vendors do some dynamic analysis in a closed proprietary form, but public knowledge and public white papers discuss mostly static applicability, with the dynamic ones limited to a few thousand samples in a prototype way. Where we do move from this look on malware sample in a static analysis tools like PE Studio, what does human analyst? It performs dynamic analysis, right, through debuggers, through detonation of malware in a controlled environment. We observe spawned processes, we observe command lines, and API calls, registry access, file system access, network connections. All this provides additional insights into functionality of malware. Most of this stuff is usually embedded within bytes, but it can be obfuscated. It can be, yeah, it is extracted during the runtime. And here comes our ability to apply dynamic analysis to ML world. We consider using emulators for this. Why? Because detonating malware in VM is costly. You cannot do this for quantities beneficial for deep learning. You need to revert contaminated environment. You need to boot up again the full operating system kernel. It takes time, it takes computational resources. And luckily, we have a great emulator thanks to the Mandiant team, research and development. They're doing a great job maintaining Speakeasy, developing it, and it basically allows to acquire dynamic telemetry just in 4 lines of code. In fact, their own data science team does research in this direction. Some insights are published in Canvas last year. So if you're interested in their work, you can take a look in this reference. So what we get from a Speakeasy emulation, basically the same information, just purely in Python. Yeah, network connections, registry access, file access, and we can get even data that is written to the files. And of course, API calls. That's only tip of the iceberg. There are memory segments, again, memory segment content, and yeah, pretty great tool, not only for automated analysis with ML, but for manual too. And what we do with this data, we basically present this model, which evaluates PE, portable executable file, from different points of view. First of all, we preserve Ember static features because they are great. We don't want to discard what we know in this direction. They do a great work in general malware distribution. However, we add additional arms. One arm focuses on API calls. Basically, we extract a sequence of API calls from the emulation report, which is the closest way, let's say, to represent what malware does on the system. In addition to that, we take a look on where malware, or not malware, but any PE file, were located on a system at the moment of execution. So we collect this data from in the wild and use to analyze our system as a contextual parameter, because there is a behavioral patterns of portable executable, and there is a contextual part that represents environment. All those 3 arms basically work as feature extractors that squeeze out the most valuable parts of their input data through the learning process, and in the end provide those called representations in an AI world. They squeeze out 128-dimensional representations of their data and provide it to the late model. We call it meta model, which actually performs the classification. It takes input from all 3 arms and basically tells from those representations whether this is a malware or benign-ware. The data set we used to evaluate this model looks like this. It's around, the training set and validation sets consist around 100,000 samples, more than 300 gigabytes of data. And the test set was collected 3 months after acquisition of training set to evaluate how model performs in the evasive, evolving threat landscape, and consists roughly of 27,500 of samples. The labels were assigned by professional threat intelligence team using manual and automated tools. And the single label clean represents a benign software, and all other labels are malicious. It's not dataset doesn't generalize well across all malware types, types, it's not so crucial for analysis of model, because we will focus only on these labels just to analyze how model works. But of course, there are other types of malware which were not included. And if you want to consider those ideas to build a more general model, don't select a specific label, select as much as possible data you can get. Clean labels are relatively more like volumetric to the malware to balance both types of data. We passed this data set through an emulator, which presumably would require a lot of resources to pass through the VMs. But yeah, with emulator, we did it relatively fast. Emulators are not perfect. They create or emulate only a subpart of actual kernel. Some API calls are not present or are not implemented. Therefore, some of the emulation is erroneous. However, as we observed, emulation error rates are not that prevailing, and they were still pretty good for our analysis. Where do we head from that? We have a file path, and we have an API call as a API call sequence. Both problems are basically the same from the ML modeling point of view. Those are these sequences. First one is encoded as a UTF-8 bytes and form a vector of integers. API calls can be encoded with a just artificial label map to where specific API call represents the specific integer. Therefore, we get basically the same input data, of course, representing different information. Then these sequences are passed to the embedding layer. What is embeddings? What are embeddings? Those come to the AI technology world from NLP, natural language processing, where we've seen that embedded tokens, when they are expanded into embedded vector space, basically what it does, it takes a narrow sequence and represents into more wider dimensional space. And those expanded values have interesting properties. For example, after training, similar tokens appear in a similar regions of this expanded vector space. For instance, cities, body parts, feelings reside in the same area. So these later layers can grasp approximate meaning of the token independent of a token appearance. Presumably something similar happens in, for instance, API call space, where sequence of API calls that can be used to inject shellcode in a thread. There are different ways to do this. They could reside in the similar vector space in the expanded embeddings. This is just speculation. We didn't verify that. It's not that straightforward to do, but presumably something like that happens. Then embedded values are passed to the next layer, which is convolutional layer. Those come from the computer vision domain. Convolutions were used to extract features from the images. For instance, this filter in the middle will extract the vertical lines from an image. And the model then performs actual convolution of the filter over the input data. Those are two-dimensional convolutions. We use one-dimensional one because they are applied over the one dimension of the input sequence. When I think about one-dimensional convolutions, the thing that comes to my mind is heartbeat, where one-dimensional convolutional layer could easily grasp the pattern that is represented in the heartbeats. Something similar is done in a file path, for instance, inputs, where one-dimensional convolutions could get n-grams like .exe or cback/win, which may later be used by later layers for actual decision boundary between benign-ware and malicious samples. Those later layers are purple ones in the architecture are basically fully connected neural network, which I assume everyone almost heard nowadays. Those are just neurons that build a nonlinear function between an input and an output. In fact, we use the fully connected neural network as our meta model too, and this is a way to build either complex decision boundary or extract valuable data from input to the output. And those are the results of our model. To emphasize again, this is done on the data that collected 3 months after the training. And how to read this heat map. X-axis represents a false positive rate, which means how many samples we fire, how many benign samples we fire alongside with the 100,000 malicious samples. And in production, you will not be allowed to push any ML model that brings alongside false alarms, because the most precious time we have is a human analyst time, and we are not allowed to like spare their analysis on false alarms. Therefore, we will focus on, for instance, this column, which represents really low false positive requirements that we give to the model. We can deploy multiple models that are super accurate in their predictions, but have low detection rates. This basically resembles what we have in rule-based or signature-based approach. They fire only on specific cases, but let through many other examples. So what we have here, if we look on separate models or arms, then we still see that Ember is the king, right? Because it extracts so many properties from the static byte blob. And again, it's a sort of a state-of-the-art, as we know right now. There is no question, it's a great tool how to apply and get a quick win for a classification. We see surprisingly poor performance of emulation on API calls, right? And this points us that we still can improve this component, and yeah, we will touch this in a minute. But the most astonishing thing from our point of view is that combination of separate modules not only improves performance like cumulatively, that we use them independently just together, but we see this emerged pattern of meta models' ability to give additional value to this input data. For instance, here we see file pass and emulation only give us like 43% samples are detected if we use them together, or even less if those samples overlap. But if we use them together and apply meta model on top, we boost that up to 77. So it's like over 30% rather than using them separately. And it's even better than this like state-of-the-art wide extraction by the Ember itself, like at least by 20%, just from file pass and just from the API call sequence. So we already can catch 77% of data. And this is something that we usually maybe don't see from a ML point of view, that it can build heuristics that we are not aware of. Just give it data, just different type of properties, just different type of like angles, and it will figure out valuable components for it. In this case, it probably takes some part of file path and some appearance of few API calls and sees that those are representative for malware, whereas the benignware with the same API calls don't have this part of file path or something like that. And of course, when using them three together, we get a fairly good detection rate with such low false positive requirement. Only one false trigger in so much like 100,000 samples. So this model already in this like prototype-ish way could be deployed in production as one of the like parts to the alerting solution for manual analysts. It still has like 14% of true negatives, but they can be captured by other means, right? We need to lap over our detections. But yeah, brief note on how adversarial malware behaves. How we read this graph, it displays two models. Let's focus only on like orange bars, which represent Ember model. And the Y scale is logarithmic. So when we constructed an adversarial malware data set from our test set, and we've seen that more than 1,000 samples were evasive on just pure model itself. When we added emulation, only 100 of those 1,000 samples stayed evasive. So like the 90% drop of evasion rates of those attacks we know. Specifically, we tested section and injection attack. And when we applied the file path as well, basically the attack yielded unsuccessful. Therefore, we proved kind of that if adversaries want to use techniques in adversarial machine learning world, they should adapt some perturbations that fool the dynamic parts of the complex heuristic. Some ideas on future work. Again, as we can see, emulation part is only prototype-ish. The performance is relatively bad if you compare directly with other models under low false positive requirements. We can consider how to improve API call model itself, but we can add a lot of more data that we were talking about previously: network connections, registry manipulations, file system. All these parts of report can be modeled, and not to monopolize or like approach on this, we publish the emulation datasets publicly. So if you want, just go to the repo and grab them, play with them. Those are JSON reports of both datasets. We unfortunately cannot publish PE samples due to privacy policy, but emulation reports are anonymized. So yeah, if you wanna play in this direction, just feel free. You have data now. Additional sources of contextual awareness can be used as like filling the epistemic gap that we have. There are parts of information that we can add for model to be valuable to segregate those 14% that it still is not able to catch. For instance, parent processes. This data is hard to acquire maybe in some cases, but for security operation centers or threat hunters, it's easy data, and you can try to model it as well. Another one is the mark of the web and download source. Of course, you know, or like digital forensic specialists here will point you that you can grab this info from ADS streams for every file, right? And you can use this as a part of heuristic, really valuable part. So those are just some ideas that if you are inspired and want to continue, those are promising directions from our point of view. Few takeaways. First of all, AI allows to model behavior. We see it rarely, at least in public research. Of course, this is done proprietary. Almost every vendor right now does this in their backend. But like scientific knowledge is really poor in this direction. There is no models that you can take and directly use pre-trained models. But we see that this can be done, and these yields are known techniques. And the benefit behind the modeling behavior that it can be applied to much wider set of data. For instance, not only P files as a byte blobs can be used for analysis, which is the case with static techniques, but data like Sysmon or ODD can be modeled as well, which represents much wider spectrum of security practitioners. Again, security operations center. You don't need to be security vendor, which is in the case in P datasets. This is usually security vendors that do this research. With the behavior, it's every one of us, SOCs around the world, that can benefit from models like this. Second, ML, basically you just need give it data and it figures itself the valuable parts. It's the pipeline that you need to build. And as we've seen, ML finds valuable components if you provide it different angles of the same question. In that case, this performance boost that we've seen by combining file path and emulation models is from our point of view, is great, and it's in fact is not artifact of this specific data set. We've seen this behavioral across validation, training, and test sets. So the same pattern emerged in every piece of data that we tested. And last but not least, what we wanted to remind everyone when we speak about ML applicability to security problems, ML is not a silver bullet. It will not replace you tomorrow and like human specialists will be out of work. It's a tool that we can use and apply. Basically, AI is a software. We are far from intelligent agents that do work by themselves. It is a tool that you can, like, as any other type of code or automation, and use it in addition to the tools you have right now. Like rule-based approach is not like substituted by AI techniques. It's an additional way to do your work more efficiently. And you can add with the small models. You don't need, you just implement one arm from, for example, this approach, and it will already can be a better detection way for you to identify some things that you need to identify. Yeah, acknowledgements to the many teams that did research that made the foundations for this work. For instance, again, Mandiant, they do a great job for maintaining Speakeasy, and their data science team does similar research. Endgame for original work on Ember. Sophos AI team showed that FallPass, in fact, improve Ember, so we were influenced by them. And guys from Cagliari University done the adversarial machine learning library that is easy to use, thanks to them and the people who support it. Yeah, that's it. Now it's the time for questions.